Hello, Coach Travis here, and today we've got sort of a big deal that we're going to talk about. I'm going to show you how you can turn a secant line into a tangent line. And after you're able to turn a secant line into a tangent line, you'll be able to solve one of the fundamental problems of differential calculus. And that is, what is the slope of a tangent line? So I hope this all makes sense, because it's a really elegant and nice idea. When you look at this and you see this all playing out, I hope you say, wow, yeah, that makes sense. That's not really that hard. And that's what's so great about this, is that this was Newton's idea, and it's a simple idea, but it's not an overstatement to say that this idea literally changed the course of human history. So this is really the exciting thing about science and mathematics, is the simplest ideas can have the most major repercussions. So you don't have to be a genius to make an impact in science and mathematics, although Newton was a genius. But if you can just, look at a problem in just the right way and understand it deeply, then you can take a simple idea and completely invent a brand new branch of mathematics. Okay, so anyway, so what's going on here? So here's what we start with. So what we're given is, we're given a function. So assume you have some function, and so we know everything there is to know about that function. So I've got some function, and then you have some point on that graph. So I know that I've got this point on the function. So I'm doing this in general. So I mean, if you look at the picture, the fact is that A is actually equal to 1. But I want to kind of do this in general. So so you can think about A as being equal to 1 if you want to, but it might be better if you think about A as just your favorite number. Think about A as being whatever number you want it to be, and then f of A is the y coordinate, so that you wind up on the graph. Okay, so we're given a function and we're given a point on the graph of the function. And then what's the goal? Okay, well, the goal then is to find the slope of the tangent line at that point. So the idea is, if you give me a function and you give me a point on the function, then there is a tangent line at that point. And we want to know, well, what is the slope of that tangent line? So that's the ultimate goal. And it turns out that's that's one of the fundamental problems of differential calculus, because the slope of this tangent line, the physical interpretation of that is, the slope of this tangent line is the instantaneous rate of change of the blue function at that point. So the slope of this tangent line has very important significance in physics, engineering, and science in general. Okay, so now let's think about, why is this a hard problem? Because you should think, well, lines are easy, and finding the slope of a line, that's an easy thing to do. We're good at finding slopes of lines. So why is this a hard problem? Why did it take Newton's brilliant idea to answer this question? And well, the idea is, think for a minute, what do you need in order to find the slope of a line? So, ultimately what you need in order to find the slope of a line is, you need 2 points. And if we think about this line, I only know 1 point on this line. I know this point right here. Now, you might be tempted to say, oh, well, don't we know the y-intercept? But the answer is no, we don't. That's why I didn't put numbers on the y-axis here. I actually have no idea what the y-intercept of this green line is. I mean, I guess I could cheat and GeoGebra tells me what it is, but I don't want to I'm pretending I don't know that. So I'm just drawing this line. This is a tangent line. And I know this point because that's what we're given, but I have no idea what any other point on this graph is. So, okay, so we've got a real problem here. I need to find the slope of this tangent line, but I only know a single point on the line. So how are you supposed to find the slope of a line if you only know one point? And the answer is you can't. So this is why Newton's idea was so revolutionary, is because people before Newton, people said, well, you know, I don't know how to find the slope of this green line. I only know one point. I'm stuck. So all right, okay. So let's see what Newton did. So what Newton did was he introduced another line. So let's get rid of the tangent line for, let's get rid of the tangent line for a minute. And he introduced this red line. So this red line, this is called a secant line. So the secant, how did he get this line? Is, well, he took the point that he started with, and then he just added a little bit to the x coordinate. So that's what this h is. So the h is like the little bit that he's adding. So to be concrete, in this case, like right now in this picture, h is equal to 5 because a started at 1 and this other point is at the x coordinate of the second point is at 6. And so in order to get from 1 to 6, you have to add 5. So the idea is he took the point that he started with and he added a little bit to the x coordinate to get a second point on the graph. And okay, so what's the good thing? What's the good news? So the good news is we can find the slope of this red secant line because we know 2 points. You know, we know this point and we know this point. So we can find the slope of the secant line. And so indeed, why don't we just write that down? The slope of the secant line is, okay, well, it's the, oops, I want to change to red. So the slope of a line is the change in y divided by the change in x. So the slope of the secant line is f of a plus h minus f of a divided by a plus h minus a, right? Let me go over that for you because yeah, the change here's y2 and here's y1. So there's y2 minus y1 and here's x1 and here's x2. So and there's x wait, did I say that right? Or maybe I got it mixed up. Here's x2 and here's x1. That's why I hate formulas. Anyway, the change in y coordinates is this, and the change in x coordinates is this. You can see that. And okay, and let's go ahead and simplify that because it has the denominator is easy to simplify. So the numerator, you cannot simplify the numerator. So don't try. At least we don't have enough information to simplify the numerator because we don't know what this function is. But the denominator, we can simplify to just h. And so this expression right here hopefully should look familiar to you from your homework. This is the difference quotient. So you had homework about the difference quotient and you might have wondered, wow, this difference quotient thing is really weird. Where is it coming from? And the idea was the difference quotient was getting you ready for this moment, that the difference quotient essentially is the slope of your secant line. Okay, so that's the good news. The good news is that we can find the slope of this red line because we know the function, we know what a is, we know what h is, so we can find the slope of this red secant line. But what's the bad news? The bad news is I don't care about the red line. I care about the green line, right? The question wasn't to find the slope of the red line. The question was to find the slope of the green tangent line. So we know the slope of the secant line, but we want the slope of the tangent line. So even though this is nice, it doesn't answer our question. Okay, but now here's Newton's brilliant idea. What if we make h smaller? So let's move this slider. I'm going to move this slider, and as I move the slider, it's going to make h smaller. So you can see that as h gets smaller, the red secant line is going to be getting closer to the green tangent line. So I hope you saw that, and I'll continue to do it again. And so pay attention as h gets smaller, watch how the red secant line gets closer to the green tangent line. So as h gets closer and closer to 0, as h gets closer and closer to 0, that red secant line is getting really close to the green tangent line. And if the lines are getting close to each other, that must mean their slopes are getting close to each other, because they're practically the same line. And if they're practically the same line, then they must have practically the same slope. And so now we just continue to let h get closer and closer to 0. And the closer h gets to 0, the closer the secant line and the tangent line get. And again, here's the moral. Uh-oh, I just lost. Okay, here we go. Okay, we can always find the slope of the secant line. This formula will always tell us the slope of the secant line. So by making that secant line really close to the green line, we're able to calculate the slope of the secant line, and thus we're able to get really close to the slope of the tangent line. And in fact, so let's see here. And in fact, you can see something interesting happens when h is 0. If I make h equal to 0, notice the secant line disappeared. And you can see that, yeah, the computer tells me that when h is equal to 0, the secant line is undefined, because essentially I'm dividing by 0. If I set h equal to 0, then you end up dividing by 0, and that breaks the computer. But as long as h is not 0, in fact, h could even be negative. Like, look at this. If h is -1, then the picture looks like this, and I can still calculate this. This formula will calculate the slope of the red line, and if I make h closer to 0, as h gets closer to 0, the red secant line gets closer and closer to the green tangent line. And so we have actually an answer to our question. If I want to get so the idea here is that the closer h gets to 0, the closer this slope of secant line will get to the slope of the tangent line. And so then we think, well, what tool do we have so we can make h get really close to 0? How can we make h get as close to 0 as we want without ever actually getting there? And the answer is that's what the limit is for. So the slope of the tangent line is going to be the limit as h goes to 0 of the slope of the secant line. So we said that Oops, I was starting to write secant line, but I want to write the formula now. So we've got f of a plus h minus f of a divided by h. So that is that red expression is the slope of the secant line. But if you then put a limit as h goes to 0 in front of it, then you get the slope of the tangent line, and that answers our question. And so we've done it. We've used the limit in order to calculate the slope of a tangent or find a formula. We've used a limit to find a formula for the slope of the tangent line. And this has a special name. I mean, we could, for the rest of our lives, we could just call this formula the slope of the tangent line. And that would be 100% correct. But slope of tangent line doesn't exactly roll off the tongue. And so mathematicians and scientists have given this a special name, and this is called the derivative. So this is called the derivative it's called the derivative of the function. It's called the derivative of f of x at x equals a, because we have to be specific. Because if you picked a different point, then you'd get a different tangent line, and then you'd get a different number here. So this thing would be called the derivative of the function at x equals a, and the shorthand notation we often use for that is we say we use the prime notation. So we would write f prime of a. That's the notation. That's the notation that we use. So these two things are exactly the same thing. So f prime of a means this limit, and that limit means the slope of the tangent line. So this derivative, this is the fundamental idea of all of differential calculus. And so, you know, as you proceed in calculus, you're going to be using this a lot. So this is like our main idea for the entire course.